Good afternoon, folks. How are you today? In the last lecture, I gave you an introduction to matrix algebra. If you took a linear algebra course, probably you learned more details. Uh, Maybe it took a couple of weeks to cover that amount. So let's see what the matrix algebra have to do with a linear system. So what is this linear system? A linear system is basically a system of linear equations. We have n equations in n unknowns. X is our unknown, and B is what is called the right-hand side is often called residual. And we are going to solve linear systems of the type where B is not equal to 0. So you may remember that we started with one equation, one unknown, where n was equal to 1, and we looked at what possible a and b could be. And we said we want to look at situation where basically a is definitely not 0, and b could have been 0 or may not be 0. But before we move on, let's see how we can write n equation in n unknowns. So first of all, instead of using unknowns such as x, y, z, we are going to use x1, x2, so on and so forth as our n unknowns. So in this case, we know A, we know B, we want to find x. So x is our unknown. Let's suppose we have two equations, two unknowns. So what we will do is we'll write them as follows. We'll write them A11 times x1 plus A12 times x2 is B1. So notice our first subscript row number is same as equation number. And second subscript is our unknown number. So our equation number corresponds to row number, and our unknown number corresponds to column number of matrix A. So when we write our second equation, first unknown times first unknown. Second equation, second unknown times second unknown is B2. So now what we do is we collect all the A elements together. And this becomes our matrix A, which is size 2 by 2. We collect all our x's together to make it a column vector. So this is x2 by 1. And we collect all the b's together. And this becomes our. So when we look at the subscript of b, that represents our equation number or row number. Okay. Same thing. The subscript on x2 is our unknown number. And in our case, since it's a column vector, is also the row number of x. Okay, so we have a linear system. If n is equal to 1, we knew one equation, one unknown, x1 is b over a, and since both b and a are finite and scalars, we have a unique solution. For n is equal to 2, you must have learned something called Cramer's rule. It's both very easy and efficient. So let's see what is Cramer's rule. Cramer's rule says, given a system A times X is equal to B, then any X is a ratio of two determinants. Determinant of matrix AK divided by matrix A. What is matrix AK? Matrix AK is matrix A with its kth column replaced by vector B, the right side vector. So you can see here in our 2 by 2 system, A times X is equal to B. So we define a matrix B1. Well, I could have named it A1, but basically first column of A is replaced by B. Here is matrix A2 or B2. In my handwriting, I call them A, but second column is replaced by vector B. So here are our ratios. Now, for 2 by 2 system, this is very efficient. But let's see what happens when we go to a n by n system. So you can see already, if we have a n by n system, we require knowledge of n plus 1 determinants. And if we use that standard recursive definition, then each determinant requires n factorial multiplications. So in total, if you use Cramer's rule, it requires so many multiplications. So let's see what happens. Suppose we were to use Cramer's rule. To solve our equations. So before we begin, to give you an idea, you may remember in one of my previous week's lectures, I spoke to you about Voyager 1 and 2, how impressed I was. These were developed in 1970s and they went on their voyage in 1977. So as I said, they had three pairs of computer. One pair was redundant or used as a backup, very low power usage. And the fastest of these computers did about 80,000 instructions per second. Let's assume it really means programming instructions, but let's assume these were what are called floating point instructions or floating point operations per second. That means multiplying, say, A times B, where A and B are both floating points. So their fastest computer could do 80,000 per second. Complicated architecture, and memory was 64K bytes only, so they could handle only so much of data uh, at a given time. If you want to learn about all these spaceships and planets, PBS NOVA has excellent series. Last year they did a whole year's worth on planets, and many of them mentioned, of course, the lunar landing too. But there are other spaceships that are mentioned there too. So please check it out. But back to our Cramer's rule. So this requires n plus 1 times n factorial multiplications. So let's suppose we were to use this on the Voyager computer, which does 80,000 floating point operations per second. And let's consider my laptop. My laptop is an i7 quad core, and it does 40 gigaflops per second. So imagine this is like almost a magnitude of a million almost. So my laptop is a million times better than the Voyager, faster than the Voyager. Let's consider, for instance, we want to solve our linear system size 10 using Cramer's rule. So we put in 10 here, and then we find out how much time would Voyager's computer take. So we calculate and we find out 500 seconds. 500 seconds is about 10 minutes. So not too bad. You could go out for a cup of coffee, come back, it'll be ready. My laptop will take about 1 millisecond before you can even blink an eye. Let's say if you go to size 100, which is quite common, already in statics, probably you're seeing problems which have got 4 or 5 truss members. Easy, we will go 100 by 100 easy. Well, it would take 1.25 times 10 to the power 96 seconds, which is 4 times 10 to the power 88 years. I don't know whether we will live that long or not, even humanity. Well, my laptop, very fast, right? Let's see, 2.5 times 10 to the power 90 seconds, which is like 8 times 10 to the power 82 years. Can make that long, right? So obviously Cramer's rule won't be the way we would be solving even semi-large linear systems. So Cramer's rule is very good for 2 by 2 system, and we will see that a little later on. I'll do some more examples. Okay, before we move on to looking at more efficient methods, let's see what we mean by solution of a linear system. So consider, for instance, we have two equations and two unknowns. 3x1 plus 2x2 is equal to 18. Minus x1 plus 2x2 is equal to 2. So let's state that in a matrix form. So we'll pick up 3 and 2, minus 1 and 2, times x1, x2 is equal to 18 and 2. Right? This is matrix A, X, B. So let's look at it graphically. So we plot x1 versus x2, and we look at our first line. So if we take x1 to the other side, notice it'll become minus 3x1, so it'll have a negative slope of negative 3 over 2. So it'll have a negative slope. So line would look something like this. So this is line 1. When we take this to the other side, it'll become positive x1, so it has a positive slope. So line 2 would look something like this. And obviously the coordinates of this point, where x1 is 4 and x2 is 3 is our solution. So let's see how we will find it using Cramer's rule. So Cramer's rule will say determinant of A is 3 times 2 is 6. Minus of minus 1 times 2 is 2. So that is 6 plus 2 is 8. So determinant of A is 8. So when we want to find x1, we will take determinant of matrix A with its first column replaced by B. Divide by 8. So this is 36 minus 4, 32. So we get x1 is 4. Let's look at x2. For x2, we'll replace the second column of A by B. So this will remain same. This will become 18 and 2. Divide by 8. So 3 times 2 is 6. Plus 18 is 24. Divide by 8 and we get 3. So this is our Cramer's rule. Keep in mind, our determinant of A was 8. So what we see is we have a unique solution. Okay. Let's look at another example. Here what we have is we have two lines. First line equation is half x1 plus x2 is equal to 1. Other equation is half x1 plus x2 is equal to half. So this is line 1, this is line 2. So if you want to write in matrix form, we'll write minus 0.51, minus 0.51, minus 0.51, minus 0.51, x1, x2 is 1.5. Okay, so graphically we look at it. x1, x2. So obviously positive slope. This is line 1. Positive slope. This is line 2. They are parallel. So we have a problem. No finite solution. Okay. So now if you look at determinant of matrix A, we find negative 0.5 plus positive 0.5. Determinant of A is 0. So we have problem when determinant of A is 0. Let's look at another example. Again, we have two lines. Minus half x1 plus x2 is 1. Minus x1 plus 2x2 is 2. So let's write this in a matrix form. 0.5, negative 0.5, 1, negative 1, 2, x1, x2 is 1 and 2. So this is our line 1. This is our line 2. Let's look at it graphically. So we plot line 1. We plot line 2. It's identical. So we have a problem now. So we have effectively only one equation, right? So effectively we have one equation. And now since both the lines are identical, we have infinite number of solutions. Or in other words, no unique solution. Okay. So let's look at determinant of matrix A. When we look at determinant of matrix A, we'll get -1 plus 1 is equal to 0. So when determinant of A is 0, the other previous situation was we had no finite solution. In this situation, we have no unique solution. So before we move on, let's kind of summarize. So if we have A times X is equal to B, n by n, n by 1, n by 1. And we are assuming B is not 0. So we find out determinant of A not 0, unique solution. Determinant of A is 0, then we have no unique solution. Okay. So numerically, we talk about, mathematically it is okay to say determinant is 0 or not 0. But numerically it is very difficult sometimes because of our floating point situation, we may have some round off error. So what if determinant is nearly 0? So I've used a word here, singular. So what does singular means? So if determinant of A is not 0, we say A is not singular. If determinant of A is 0, we say A is singular. So what about nearly singular? Determinant of A is nearly 0. A is nearly singular. Question would be how close to 0? But let's again take two equations, two unknowns. So let's suppose we have one equation, minus 2.3 over 5 x1 plus x2 is 1.1. Then we have minus half x1 plus x2 is 1. So we write it in our matrix form, minus 0.46, this is minus 0.46, 1, minus 0.5, 1, x1, x2 is 1.1 and 1. So let's look at it graphically. So I plot line 1, I plot line 2, find this intersection point. And again, I can use Kramer's rule to find my point exactly. And it turns out this is 2.5 and this is 2.25. Just like what it is shown here. Now, I'm going to leave it as it is and go to the next slide. So I'm going to make just a tiny bit change. I'm going to change this number by tiny amount. So I'm going to change this to 1.05. So change this to 1.05. Suddenly, as I change it to 1.05, what happens is x1 moves to 1.25. and x2 moves to 1.625. So what is happening is, as soon as I move these lines slightly, so this line moves parallel slightly, this line moves parallel slightly. Actually, I changed only one of the lines, but you can see if these nearly parallel lines, if I just move them slightly parallel to themselves, the intersection point is going to change quite a bit. So that is what we mean by ill conditioning of the system. So let's see what our determinant here is before we move on. So when we take determinant of A, determinant of A, this times this minus this times this comes out to be 0.04. So it looks low. We had 8, remember, then we went to 0, it's 0.04. But really, if I multiply both sides of the equation by 100, this will become 4. If I multiply it by a million, this will become like, I'll have to calculate it, but you can see it becomes quite large. So I could just make determinant of A as large as I want it to. Of course, my conditioning is not going to become any better. If the lines were nearly parallel, they will remain nearly parallel. So in order to find conditioning of a system, what we do is we normalize. So if we have matrix A, we normalize it. So we get A normalized. How do we normalize it? Suppose we have a matrix. It has a row. We take all the elements on this row, square them, sum them, and then take the square root of it and divide entire row by that normalizing factor. Same thing we do for next row, same thing for next row. Once we get a normalized matrix, then we take its determinant. So what the normalization process does is makes its determinant's magnitude between 0 and 1. So determinant can be positive or negative. We don't care about usually the sign. So we say this determinant can be less than or equal to 1 or greater than equal to 0. It is in the range 0 to 1. If it is closer to 1, we say our system is well conditioned. That means any small errors, round off errors we make won't affect our solution a lot. On the other hand, closer to 0 we say it is ill conditioned. So of course, this is very subjective. For our purposes, what I will do for our class purposes, we will use 0.5 midpoint, and we'll say if it is 0.5 or better, well conditioned. If it is less than 0.5, ill conditioned. But that's just for our classroom test and quizzes. There is no such boundary between ill and well conditioning. Well, let's go back and check how good our conditioning was. So this was our first problem. So our matrix was 3, 2, minus 1, 2. So we normalize it. So first example, our matrix A is 3, 2, minus 1, 2. So our normalizing factor here would be 3 square plus 2 square, square root. So we will get square root of 13. Here 1 square plus 2 square, so we'll get square root of 5. So we divide first row by square root of 13, second row by square root of 5, and we calculate these, we'll get these numbers. So we take our determinant, and it comes out to be 0.992. So you can see it's pretty close to 1. So we have a well-conditioned system. Let's consider our fourth example. Matrix A was minus 0.46, 1, minus 0.5, 1. So our factor 0.46 square plus 1 square, 0.5 square plus 1 square. So this is 1.101, 1.118. So we divide first row by 1.101, we divide second row by 1.118, take its determinant, and this magnitude is 0.032. So you can see this is much, much less than 1. So therefore, this is ill-conditioned system. And that's what we found. Lines were nearly parallel. But of course, when we go to n beyond 2, we cannot think in this terms of lines. So here is the basic fact. You can do nothing to improve the conditioning of a system. All you can do is not make it worse. So when you are computing with ill-conditioned system, every time you do some computation, you have a round-off error, you have a potential of making your system worse. So in such a case, you need to be cautious. You need to use very, very careful scaling and pivoting strategies. So I'll explain you these two words, scaling, pivoting, later on. Okay, so let's see how we solve a linear system. Before we move on, something I want to mention. So we have our system A times X is equal to B. We know A, we know B, we want to find X. Obviously, we want this A to be not 0. Let's look at matrix B. Matrix B could be 0. So if matrix B is 0, we have a system AX is equal to 0. So first of all, it has a trivial solution. X is equal to 0. It turns out that this system may have non-trivial X not equal to 0 solutions. And they may exist if and only if. So this is a mouthful of a word. So what we do is we shorten it and misspell if. Say if and only if determinant of A is 0. That means A is singular. So if you take some other math courses, these are called eigenvalue systems. Okay. We are going to be solving problems only when b is not 0. So we'll always write ax is equal to b. And here in this case, we just found out unique solution exists if and only if, remember misspelled, right? Determinant of A is not 0. That means we want A is not singular. And we said we have a problems when A is nearly singular. Right? We have all kinds of conditioning problems. So we have methods to solve this problem. Ax is equal to b not 0. There are two categories of methods. One called exact methods, like Kramer's rule. If we do it with the exact machine, we'll get an exact answer. Of course, there's a problem. Number of multiplications is proportional to this factorial number, which becomes huge when n is large. That's why Kramer's rule we use for n is equal to 2 only. Even for n is equal to 3, 4 or beyond, it really becomes very expensive. So we use one of these direct methods. These direct methods have number of multiplication proportional to about n cube. We usually don't worry about the factor up front. Usually it is like 1/3 or 1/4 or something like that. It all depends on programming style. But let's see, let's go back to how good these methods are. So I'm going to find the page where we looked at the time. So let's go back to this calculation we are doing. So if we use direct methods like elimination methods, so these all methods, Gauss, LU decomposition, matrix inversion, they are all elimination type of methods. Number of multiplications required is only about n cube. So when I use n cube over 3, for instance, again, this number is immaterial. Let's look at how much time would Gauss elimination take. So remember, for our Voyager computer, Kramer's rule took 10 minutes. If I use elimination method, that old computer would take only 12.5 milliseconds. So blink of an eye. My computer, using elimination method, 25 nanoseconds. Okay, how about this? 10 to the power 88 years. Even the old computer would take only 25 seconds. Big improvement, right? How about my computer today? For a system size 100, I can do it in 25 microseconds, right? So therefore, when we use the spreadsheet, we will easily be able to do 10 by 10, 100 by 100, just sitting. We won't have to even twiddle our thumbs or go for a cup of coffee. So that's how good they are. You will see another category called iterative methods. In iterative methods, because they are iterative, number of multiplication requires is n square per iteration. So that means if we converge in less than n iterations, these iterative methods become efficient or comparatively efficient. So imagine, for instance, the size of our system n is 1,000,000. So if we converge in less than 1,000,000 iterations, and 1,000,000 iterations is huge many, you will see often we are converging in something like 100, 200 iterations, even to get 7 digits. So you can see for large system, these iterative methods become very attractive. There are some other further efficiencies built in, especially when we are solving engineering problems. Engineering problems have certain matrices, have certain properties that we can exploit to take further advantage of these iterative methods.